Hello everyone, welcome to section 3.5. In this section we're going to talk about optimization. So when we mention optimization in a mathematical sense, basically what we mean is in business, economics, and any other real world application you can think of, we often want to find the optimal condition where a specific quantity is maximized or minimized. Optimization is the process of finding this maximum or minimum. Notice when you see optimization, your brain should be thinking maximum or minimum. And we've done this using that first derivative test. And that's exclusively what we're going to use in this section when we talk about finding a maximum or finding a minimum. We're going to use that first derivative test. So we're going to get a lot more mileage out of that. Remember, the first derivative test tells us if we have a maximum or a minimum value at a given point. So that's what we're going to do. Say we're dealing with profit. We always want to try to maximize our profit, right? Or if we're talking about costs, we want to minimize our cost. So these are the types of things that we need to be able to find. Again, I just want to do a couple problems. Optimization problems are known for being a little difficult, a little tricky. There are some that are just very mechanical and very easy, right? Just plug and shove, you're done within a minute or two. And then there are some that it really takes a while to wrap your head around what they're asking. You have to come up with the right function, then you have to differentiate that function correctly. So they can be easy, they can be challenging. They range the full spectrum there. So if you're practicing some of the homework problems or some of the exercises in the textbook, if you do number 1, do number 2, do number 3, do number 4, and go, oh, these are easy, let me try number 25. Whoa, that's a whole new world, right? If you even just go to number 7 or number 8, it's probably way more challenging than number 4 was. So the difficulty starts to ramp up with all these problems. But essentially, what it all boils down to is differentiating, finding that max, finding that min. Right? That is what optimization is for. And I mentioned profit. I think that's a good place to start because that's something that we can really grab a hold of. We can talk about profit. So first, I'll say that recall. Let me not use blue here. And I'll switch it up to black. Let's say recall the profit function is given by P of x is equal to R of x minus C of x, where R of x is the revenue from producing X number of units. C of x is our cost from producing X number of units. So X just counts up how many units we've made, produced and sold to get our revenue and our cost. So let's say let's look at an example where we'll let the revenue equal 50x. I don't know, I have it written down. Yeah, that's 50x minus 0.5x squared. So let's say we have this given revenue function and we have a given cost function as well. C of x is going to be equal to 10x plus 3. And let's see if we can find the maximum profit and the number of units needed to achieve that profit. Now, so let's say we're given this task. All right, this is what calculus is all about. Hey, can you find the max? Can you find the min? Well, notice what we're trying to do. Again, anytime you see that word maximum, that's the thing you need to differentiate and set equal to 0, get your critical values, and find that max or min. So here I see the word find the maximum profit, which means right off the bat, I need my profit function so I can differentiate my profit function, so I can set that derivative equal to 0, so I can find that critical value, so I can get that maximum or minimum. You see all the steps in the process? Right, so it's just like a chain of events that happens. You need a function, you need to differentiate that function, set it equal to 0 to get the critical values, plug those into your first derivative test, pick up where the max and min occurs. Now it asks us for two things. First, find the maximum profit. So we're going to have to see what that is, what the output is for our profit, the maximum value, and the number of units needed to achieve that. That means first I need to find X, those number of units, and then plug that number back into my profit function, and it will reveal the maximum profit. So let's do that. Let's go through this process first by setting up P of X, which I have up there. It's the revenue minus the cost. So in our case, it's going to be the revenue, which was this function, 50x minus 0.5x squared, minus the cost. Now I have to subtract all of my cost, not just the first piece, right? I'm not subtracting the rest of my cost. Now I'm subtracting my entire cost with the parentheses there. I can see that all of my costs subtracted. Right? Don't just subtract the first piece of your cost. Make sure you subtract all of your costs. So here's our profit function. If we simplify it a little bit, 50x minus 0.5x squared minus 10x minus 3, which means our profit function, I'm just going to go ahead and combine these two terms, 50x minus 10x. And I'll write it in descending order for the powers. You don't have to by any means, but maybe just to keep it a little organized here. Here is our profit function. All right, so we've got our profit. This is the thing we're trying to find the maximum for, which means I need to find P prime. All right, so again, you see the steps in the process. I finally got my profit function. Let's go ahead and differentiate that and see what we get. P prime of x is going to be given by negative 0.5 times 2 is negative 1, and I reduce that power by 1. This is just a simple polynomial, so I'm using simple power rule there. I get negative 1x, I'll omit the 1, plus 40. What do I do with this? Well, this is my derivative for profit. I set it equal to 0 so I can find my critical values. So now I'm going to say, well, let's add x to both sides so we can get this done pretty quickly. 40 is x. What have I just found? This is the number of units. This is the number of units needed to maximize profit. I have already answered the second part of the question. I've already found the number of units that I need to maximize profit, right? Number of units needed to maximize profit? Yeah, it's 40. Done, right? Well, not done with the whole problem, because it also asks, what is that maximum profit? Right? So I still have a little bit more to go within the process. I found my critical value, x equals 40. I can take that critical value, plug it back into my profit function, and see what profit I get. So now I'm using this number. Since I know this is a maximum, I can plug this into my profit function, aka I can find P of 40, and it will tell me the output, what the actual maximum profit is. So let's do that. Negative 0.5 times 40 squared plus 40 times 40 minus 3. There's my profit function, but there's my profit function with 40 in there. And just to save time, I went ahead and did this in the calculator, and I got $797. So now we have figured out that our maximum profit is 797 when we produce 40 units. So you can see that a nice application like this gives us, exactly how many units we want to produce. It might not be to our benefit to produce more than 40 units. Maybe if we're, I don't know, say we're making, I don't know, T-shirts or something, right? If we decide, oh, you know what, okay, maybe I'll make an extra 10 T-shirts. I'm not going to maximize my profit. Know what this function looks like. This is a quadratic function for my profit, and it has a negative leading coefficient. So this thing is a quadratic with a negative leading coefficient. It has a certain maximum. So if I want to maximize my profit, I shouldn't make too little because I will never hit that maximum. And I shouldn't make too much because my cost is going to consume all of my revenue at some point. I won't make enough profit to stay alive, or to make any usable money back. So again, profit is one of the biggest applications that we have in this section. But I want to do an example, actually I've got two picked out. I want to do an example where it's even boiled down to something a little more simpler. So when you study this a little deeper, there are whole courses on optimal control theory where you have tons of variables. We just had one variable, X, the number of units. There are courses that you can study where you have tons of variables, X, Y, Z, omega, and then you have to kind of pick which variable you want to optimize, because sometimes optimizing one kind of makes the other one not so great, and then you say, oh, well, let's fix that. Let's optimize this one. Oh, wait, now this one's not really that great. Well, you got to kind of pick one and see which one's more important. Do you want to minimize your cost more than you want to maximize your revenue, or do you want to maximize your revenue more than you want to minimize your cost? But so you can see that even that can get a lot more complicated. But to kind of boil it down, what they do usually when you look at these optimization problems is you look at one function and then you look at the constraints on that function. So let's say we say, let P equal X times Y, where P is just the product of two numbers, right? And they're not technically the same number right off the bat. We don't know that, so we just call them different numbers. So let's say that P is equal to X times Y. Now let X plus Y equal 50. This is what we would call a constraint. Right? We have to meet this. Should be an I there. So we have to meet this criteria when it comes down to how can we look at these in terms of we're restricted to this value. So when we're restricted to this X plus Y equals 50, and we look at this objective function, P equals X times Y, how can we maximize the product? That's why they call it P, X, Y. Right, we need to find the X and Y values that will maximize this product. So again, not even like a full application to anything in the real world. This is just a general function, P, and it's constrained by this. The sum of these two numbers has to be 50. I don't know that X is 49 and Y is 1. That might not maximize the profit, right? 49 times 1 is only 49. Maybe X is 2 and Y is 48. Ooh, okay, that makes that a lot bigger because 48 times 2 is, it's larger. The point is we need to find P prime because our eyeballs go to this word maximize the product X and Y. That's this guy, P. So we need to find P prime, and we need to figure out where it's going to be maximized. Now, P is not a function of X. It's a function of X and Y. So first, what we need to do is hold off on this and say that, notice, X plus Y equals 50 implies Y is 50 minus X. So now I can solve for y. Since now I know what y is, I can plug that into my function p and get a function strictly of x. Thus, p equals x times y is the same thing as p is equal to x times 50 minus x, right? I'm just simply making that replacement y goes where y was, which tells me that p is equal to 50x minus x squared when I distribute. I'm simply distributing so that I can now say that p prime is going to be equal to 50. This is strictly a function of x minus 2x. It's strictly a function of x, so I just use the power rule. And if I want to try and maximize this, then what I have to do is take this and set it equal to 0. Maximum will occur when p prime, which is 50 minus 2x, is equal to 0. So this is what I want to do. I want to set this equal to 0 and find my critical value. What we can do is probably just add 2x on both sides here. This will tell me that I get 50 is equal to 2x, which I can divide by 2 on both sides. That'll tell me that 25 is equal to x. Well, if 25 is equal to x, and we went back and said this is y, I can find y very quickly. Y is 50 minus x, which is 25, which means y is 25 as well. And this should make sense. When we want to maximize a product, we square it. That's exactly what we're doing. 25 squared is the largest value we can get, such that when we add those two numbers, we also get 50. And you might think, well, I can multiply 50 by 50 and get a larger number. Yeah, but 50 plus 50 is not 50. So you're not allowed to just pick any numbers you want. You're constrained to those numbers having this property. They must add together to get 50. But then you have to pick the two numbers that maximize their product. And in this case, it's a square, right? If we square 25, that's the largest number we can get, but still keep that number such that when we add these two separate numbers together, we stick to 50. And we don't go past 50. Obviously, we don't want to go under 50 with the sum because then the product would be smaller. So again, a little more mechanical. I want to do another one like this with a different constraint, though. And here, P is not the profit. The book just used P for product. In fact, this one I'll change it up to a different letter. Let's say Q. Let Q equal X times Y. And let X minus Y equal 4. All right, so we've got an objective, and we've got a constraint, and we want to minimize the product X times Y. All right, so again, we see the word minimize, same thing as saying maximize. All right, we want to go through this same process to try and find this minimum. Well, if we want to do that, then obviously we need Q prime. Right, so again, Q is X times Y, not a function of one variable, and that's all we know how to deal with is a function of one variable. So again, first, notice our constraint, X minus Y is 4, which means negative Y is 4 minus X, if I subtract X on both sides, which means positive Y is, I'm going to swap those around, negative 4 plus x, which is x minus 4. So this is what I want to use in order to replace in my function. Thus, q equals x times y is the same thing as q equals x times x minus 4. Which means that q is equal to x squared minus 4x. So now we've got a function of x. We want to minimize q. So at this point we need q prime. Q prime is equal to 2x minus 4. What do I want to do with q prime? I want to set it equal to 0 so that I can find my critical values. This one's not too terrible, right? We'll add 4 to both sides. Q prime is 2x. Or sorry, we're done with q prime of 2x minus 4 equals 0. So 2x equals 4. Divide by 2 so that x is equal to 2. All right, we found one of these numbers that will help us minimize this product. Well, again, recall that we already found y is x minus 4. So let's go ahead and reuse that y equals x minus 4. Well, x was 2, which means y must be negative 2. So those are the two values that will minimize the product, but they still sum to, or sorry, their difference is still 4. So I've got a positive 2 for x, and then I'm going to subtract a negative 2, which is still a positive 2, which is 4. And if I multiply 2 times negative 2, I get a negative number. So I'm minimizing my product. Right? If these were both negative, I'd get a positive number. If these were both positive, I get a positive number. So one needs to be negative, one needs to be positive in order to hit that minimum value. Right? Negative numbers are definitely less than any positive numbers. So we're good there. So again, just more mechanical process. But let's get back to the real world. Let's say we want to look at something that has more of an application that we can see. We can draw a picture for, we can wrap our head around it a little better maybe. So this one, and this one I'll tell you, I'm pulling right out of the textbook. It's number 16. So it's an even numbered problem. And it says, a rancher wants to enclose 2 rectangular areas near a river. The rancher has 240 feet. The book says yards. The rancher has 240 yards of fencing, or just of fence. And they want us to find the largest total area that can be enclosed. Find the largest total area that can be enclosed. So again, if you don't want to rewrite all this, it's number 16 in the book. Well, first things first, when you get to a problem like this, the book's nice, it gives you a picture, but if we don't have a picture, we draw a picture every time. So let's say we have 2 rectangular areas that border on a river. There's our rectangular areas bordering on a river. We have 240 yards of fence. How can we get the largest total area that's where you see the word largest, you should be thinking maximize, right? Which means you should be thinking, I need to find a formula for area, find that derivative, set that derivative equal to 0, find the critical values, boom, there's my maximum area. All right, so again, it's just steps in the process. Get a function, differentiate the function, set it equal to 0, find those values. So what I'm going to do is set it up as these lengths I don't know. It has to be a rectangular, right? Two rectangular areas. This length is not x, and it's not guaranteed that these are squares. I don't know that right off the bat. So I don't know what this length is, so I'm just going to call it something else. I'm going to call it y. Now, if I look, the perimeter of all my fencing, I'll just call it p, is going to be x plus x plus x plus y, right? I need x fence, x fence, x fence, and y fence. That's how much fence I'm using. All right, so there's all my fence, and all my fence that I have to use is 240 yards. So this has to be equal to 240 yards. 3 of these lengths, and this one length here, is 240. It's going to border the river, so he doesn't have to fence that side, which is nice. That's not what I'm trying to maximize, right? I don't need to maximize the amount of fence. I already am restricted to 240, right? I would just use the full 240. I want to maximize area, so I need a formula for area. In this case, my area is like my length times my width, right? I'm looking at this total area in here, which in our case is going to be x times y. Gives me the whole area in here. Yeah, maybe this fence in the middle eats up a minuscule amount of area. We're going to ignore that. So let's see if we can maximize this area. Again, this is what we need to maximize. We need a derivative for this. This has 2 separate variables in it. This is not a function of x. So what I do is I use my perimeter p, my restriction, that's my constraint. I use that constraint to subtract 3x and get y is equal to 240 minus 3x. This is what I can replace here for y and say that my area is given by the formula x times, well, this is now y, 240 minus 3x, which means my area function becomes, and again, I'll write it as a polynomial just so it'll be a little easier to differentiate, 240x minus 3x squared. There's my area. That's the thing that I want to be able to differentiate, which is straightforward. It's a polynomial. So let's just do that. Differentiate term by term. I get 240 minus 6x for a prime. What do I do with this a prime? Critical value, set it equal to 0. I want to know where this thing is equal to 0. It's a derivative. When it's equal to 0, I'm either hitting a maximum or hitting a minimum. Now, I'm guaranteed to hit a maximum because look at this. Negative leading coefficient. Right? This is not the leading coefficient. This is a quadratic. The leading coefficient is negative, so it's a parabola that opens down. So I'm guaranteed to hit a maximum. So let's do that. Let's set this equal to 0. Well, let's just add 6x over to the other side so that we can quickly divide by 6 and say that 40 equals x. Right, so this is our x value, aka it must be 40 yards. Right? Right, so we found out that x has to be 40 yards. How can we find y? Right, again, look at what the problem asks. Find the largest total area. 40 yards is an area. That's linear. Right? I found one of the dimensions. I need to find the other dimension so that I can plug it in and find the area. So let's go find y. Well, look, we already solved for y. That's one of the benefits of doing this. I can just plug 40 in right here and I get y. So we'll just say, I'll tweak over here. Recall, y is equal to 240 minus 3 times, well, in this case, x is 40. So that means y is equal to 240 minus 120. So y is 120 yards. Now we're ready to finally answer the question. Thus, the largest total area that can be enclosed, I'll just say the largest area, is A equals x times y, which we found to be 40 times 120, which is 4,800 square yards. There we go. And now we've got our final answer. So again, we don't know right off the bat, what the shapes of these are. We don't know that they're, perfect squares. We can't really tell that. We've got to set it up in such a way that it's rectangular, given what they're telling us to do. Once we set it up into two separate regions, we don't know what the length is, so we have to call it something else. We have our objective, right? This is our objective, is to maximize this. We have the constraint, we're stuck to 240 yards, and we use the picture to build a function for that constraint, and then replace y with what it is in terms of x. So I would say on the scale of, 1 to 10, let me make sure I click on that. On a scale of 1 to 10, when it asks for, how easy or how hard are these problems? Make sure that's there, yeah. On a scale of 1 to 10, when it asks how easy or how hard these problems are, this one's probably, I don't know, maybe a 4 or 5. It might feel like a 6 at first. So let me do one of what I would consider for this class maybe a little more difficult problem, and then we should be good. We should be ready to go. So if you look on the screen on the bottom right, I have the textbook pulled up, and what it is number 23 I'm looking at. Again, I'm going to do the one with the picture just so it's a little more helpful. So I'm looking at number 23, coming from that textbook. Hope that's capturing all of it. And hopefully you can read it there. So I'm looking at this one, number 23. And it says, minimizing surface area. Open air waste management is designing a rectangular construction dumpster that will be twice as long as it is wide and must hold 12 cubic yards of debris. Find the dimensions of the dumpster that will minimize its surface area. So I'm going to redraw a similar picture. Keep in mind, this is what they're labeling as x. This is what we don't know from here to here. It needs to be twice as long, so this is 2x. Yeah, it looks a little stretched out in my picture. But we also don't know how high this thing needs to be, and they never said this was square. So this isn't x and x. We're not allowed to say that. We have no right. So I'm going to call that y. So the only thing that they tell us that we can infer is that the length is twice the width. Well, we don't know the width, so that's our unknown x. We can double x to get the length, but we still know nothing about the height. We're not allowed to say that the height is also x, or it's 2x, or it's 3x, or it's half x. We're not allowed to say that. We don't know. So what we do know is that we're trying to find we're trying to minimize the surface area. Right? So our goal in this case is to find the minimum amount of surface area. All right, you see that word minimum. That means you're trying to minimize surface area. I'm going to use SA for surface area You can just use S. Now let's do that. Let's just simplify it to S. One less thing to write. So let's call this surface area S. How can I find the surface area? Well, first things first, I need to find the surface area, I'm going to draw a little another line here, of the front and the back, right? So there's a back here that I need to find as far as surface area, which will be X times Y, but I need two of them because there's also an X times Y in the back. All right, so this is for one front and one rear. Now I also need to find the bottom, right? There's a bottom to this dumpster or container. So I need to add that surface area on. That'll be X by 2X, right? The width by the length gives me the bottom surface area, X times 2X. I also need to find the two sides, right? So I've got one bottom. I need two more sides so I can complete this thing. So I need this side and this side, which will be 2x by a height of y. Right? Length is 2x, height is y. But I have two of them. Right, so this is our two sides. Plus, I don't need a top. Right? There is no top. It's a dumpster. We need to be able to dump things into it. So it's an open top. So to make this a little bit nicer of a function, right? I'm doing x times y for the front and x times y for the rear. That's just 2xy. One of the bottoms will be x times 2x. Well, that's 2x squared. I need two of the sides, 2x by x, and then the other side is 2x by x. 2x by y and 2x by y, but I need two of them. So I've got 4xy, and no top. The top's not there. We can make it a little bit cleaner one more time. These are like terms. So our surface area is given by the formula. This will be 6xy plus 2x squared. This is what we need to minimize. But there's a problem. Do you see the problem? There's this extra y in there. I don't know what y is. So what I need to do is look at my constraints. Now, if you go through and read the problem, it says it must hold 12 cubic yards of debris. When you think about something cubed, you're thinking volume, right? So we've got a constraint that we need to cook up, and it's not immediately given to us. They say that the volume, which is x times 2x times y, right? When I find volume, I just do like length times width times height. This will be the volume, which will be the same thing as 2x squared y. That constraint must be equal to 12 cubic yards. All right, so there's my constraint. I have to say that the volume 2x times y must be equal to 12 cubic yards, where x is yards, this is 2x is yards, y is yards, so I get yards cubed. Well, let's solve for y so that we can plug it in here. Right? I need to use my constraint to say that if 2x squared times y is 12, I can divide both sides by 2x squared, assuming x isn't 0, right? I don't want to divide by 0, but if x is 0, I have no dumpster. So it's very clear that x is a non-zero number. So y is going to be 6 over x squared. I have now found y. I can now plug that y into my surface area function. I'm done with the constraint. I can now work with my surface area, find this minimum surface area. So let's say S is 6 times x times 6 over x squared, and I'm replacing y, plus 2x squared was fine from the get-go. This tells me that S is equal to 36 over x plus 2x squared. I need to differentiate this, so I'm going to cheat a little bit. Instead of dividing by x to the first power, I'm going to multiply by x to the negative first power. And that's just my opinion that it'll be slightly easier to differentiate at this point. And here we go. Now we're going to find the derivative s prime. This is what we needed all along. Look at all the work we had to do to get to this derivative. And then once we get the derivative, we still have to set it equal to 0. So we're not even there yet. This will be negative 36x to the negative 2 power. Again, I did this so it's easier using power rule. Negative 1 multiple comes down. I subtract 1 from negative 1 to get negative 2 as my power. This one's a little more straightforward. 2 comes down. 2 times 2 is 4. And x to the first power. I have to set this equal to 0 and find a critical value. So that's what I do. This piece is now equal to 0, which means I'm looking at negative 36. I'll move this back down as x squared in the denominator plus 4x equals 0. Okay, if this is undefined at x equals 0, I get a critical number, but we just said x can't be 0. So I don't care about that critical number x equals 0. Why? Because if x is 0, my width is 0, my length is 0, I have no dumpster. And so obviously x is non-zero. So let's multiply both sides by x squared so that we can get it to cancel out on the left there, and I won't have to deal with my denominator anymore. When I multiply by x squared, I have to distribute across this addition, leaving me with x squared divided by x squared, cancel each other out, I get negative 36. X squared times 4x, I get plus 4x cubed. Right hand side, 0 times x squared is still 0. So now I can add 36 over, and I can get 4x cubed is 36. I can divide by 4 to get x cubed is 9, which means x must be equal to the cube root of 9. X was my width. I just found how wide my dumpster needs to be. Now I'm in what we call the home stretch. And I have this, I have it written down, I approximated it somewhere. There it is. So I have this written down, and it's okay to approximate it at this point. This is about 2.08 yards. So it's about 2.08 yards wide. If I want to find the length, I would just double it. So 2x is going to be, and again, we can just approximate it at this point. 2x is the length. It'll be approximately 4.16 yards long. So we needed to double that in order to get the length back. So check. We still need to find y, right? We need to find the dimensions that will minimize this dumpster. So we don't even know how tall it is. We know how wide and how long, but we don't know how tall it is. Well, you can go find it pretty quickly just by remembering y was 6 over x squared. Y was 6 over x squared, which in this case is just, again, approximating it, plugging in that 2.08 into x, I get, if I did it somewhere, maybe this was the one I didn't do, haha. So let's do y equals 6 over 2.08 squared, just to get a nice approximation on the height. I wish I had that on-screen calculator, but we'll make do here. I get 1.386. Let's round it up to 1.39 yards high. There we go. Now we have all three dimensions. And again, our volume needed to be 12. That'll be about 12. Again, we're approximating, so it's not going to hit it dead on. If we wanted an exact answer, we would have to leave that, right? Cube root of 9. 9's not a perfect cube, so we can't really take the cube root nicely. It's a perfect square, but unfortunately not a perfect cube. So if we wanted the exact answer for 2x to double it, we would need 2 times the cube root of 9. Yuck, right? Just yucky, but it's doable. Same thing here. If we wanted the exact answer for y, it would be 6 over the cube root of 9 was x, and we need to square that. Again, yuck, it's like a cube root of 9 squared all in the denominator. So exact answers, they can be a little yucky. They will work out back to 12, but it's okay to approximate it at this point. It's a real-world application, right? You never go into Home Depot and say, hey, can I get 6 over the cube root of 9 squared feet of wood, please? Right, they're going to look at you all strange. So you can approximate at that point and say, hey, can I have 1.5 yards or 1.5 feet of something? And they go, yeah, sure, I can cut that right up. And then you just need to trim it back, obviously. But that's it. Again, just to give you like a full screenshot there of the whole shebang. Optimization problems, again, they range from very straightforward mechanical to pretty tricky. I would consider this one a little tricky, as there's quite a bit involved. So try a full range of them. I may even end up, if you guys have some questions, this is one of those sections where students tend to have a lot of questions, because think about in terms of word problems. People go, oh, I don't like word problems. And then fractions, oh, I don't like fractions. And then calculus, oh, calculus is hard. This is all 3 of those things combined, right? You're using everything all at once. So it's a little overwhelming when you get to the trickier problems. I may make like a supplementary video and cover like another 2 or 3 or 4 problems just to kind of help you guys out. I might even work out one of the problems on the study guide and work that out for you. But I want to give you guys some time to try it first, and then after you try it, if I start getting some questions, I'll say, okay, well, I got 5 or 6 of the same question. Obviously, it's time to do this problem and walk you through it. So, keep studying, stay happy, stay healthy, and just end the video here so it doesn't get too much longer. Thank you very much.